Okay, we're rolling. So, welcome to test number 2 review. I'm Chris Martin, and I will be your spiritual guide through this journey. Just like last time, the test has exactly the same format. So, you'll have all 90 minutes to complete it, your entire lab block. You'll have 15 multiple choice questions, each worth 2 points, one lab based question worth 10 points, and 5 free response questions, each worth 10 points as well, which means if you sign the honor pledge and sign your name, you'll also get 10 points, which is pretty exciting. Um, and just like last time, bring a sheet of paper front and back. Make sure that it's handwritten notes that you've got on there, um, and that it's not just copied and pasted from something. And just like last time, make sure you bring a calculator that is not internet capable, as in not your phone. And yeah, that's the thing. Have you all know like calculator technology has not changed from when I was in like 5th grade, I think is when I know TI doesn't have their we got it right with the 84s, man. Let's just stop at this point. Um, yeah, probably. Or 89s. I remember when I was in calc, I had to use a TI 89. That thing was primo stuff right there. All right. And let me know ahead of time if you need to borrow a calculator. I'm not as worried about it this time because we didn't run out of calculators for any class period, so that's good news. But still, to ensure that you get it, probably a good idea to let me know. Once again, I've already put this whole PowerPoint on Canvas. So if you miss something, either A, go back and watch the video, or B, um, take a look at this document, this PowerPoint on Canvas. But the first thing that you are going to need to know will be Newton's first law of motion. And this is basically saying any object in motion will stay in the exact same motion unless it's acted on by an overall net outside force. So objects at rest stay at rest, objects in motion stay in the same motion. That means the same velocity and the same direction, unless they're acted on by an outside force. Here's another way of wording it. It's basically saying no, if the total force is 0, you have no acceleration. Because that's really all that acceleration is a change in velocity. Anytime I change velocity, it means I'm either changing speed or I'm changing direction. So in this first instance, if I go in the same motion, stay in motion, that means I've not changed my speed and I've not changed my direction. I've not changed my velocity. Total force is 0 newtons. Staying at rest, my total velocity is 0 and it stays 0. I've not accelerated. My total force is 0 newtons. This is the law of inertia. It's just an object's tendency to keep doing what it's doing. Yeah. Most things in the universe are lazy. They don't want to change what's happening at this point in time. They're just going to keep on trucking. And they are happy with that until some force comes in and pushes them and makes them change what they're doing there. You'll need to know Newton's second law. And if you don't have Newton's second law already committed to memory, this is one equation that you will have memorized before you leave this class. F equals ma. Basically, Newton's second law is just like the reverse of Newton's first law. If there is a force, there is an acceleration. Whereas Newton's first law was no force, no acceleration. Whoops. And again, this is a net total force. So me right now, for those of you watching at home, you can't see me. I'm doing something awesome. I'm standing still, motionless, meaning the total force on me is 0. Now, that's not to say I don't have any forces at all acting on me, because I still got gravity pulling me down, and I still have normal force pushing me up. But in this instance, they're canceling each other, so my total force is 0, and that means my acceleration is 0. Once I actually start speeding up, friction pushes me along the ground, then I get an acceleration because I have a total force that is not 0. So F equals ma. Remember that forever. By the way, for those of you in calculus, this is pretty much the only equation you need, and every other equation that we use in class, well, almost, kind of originates from here and then uses a bit of calculus to work its way to something else. But this is pretty much the starting point of physics. Then you've got Newton's third law, which is every force has an equal and opposite reactive force. Which means if a truck hits a mosquito, the mosquito exerts the same force on the truck that the truck exerts on it. If I hit a tennis ball, my racquetball exerts the same force on the ball than the ball exerts on my racket. A lot of times people forget this law simply because when we do free body diagrams, we only look at one object at a time. And when you look at only one object at a time, you don't see the equal and opposite reactions. For example, a free body diagram of myself, looking ever so stunning. Look at that little headpiece cutting into my forehead. And I'm smiling off to the side. That is... And when you draw a beard as red, that just makes it terrifying. So if I'm standing here like this, the forces acting on me are ground and normal. Now, all that I show you is that normal force exerted upward on me. Meanwhile, the floor is feeling that exact same normal force, but downward, because I'm pushing on it downward. Except you don't look at this in a free body diagram, because generally you only care about one object at a time. So this is what the third law means. If the floor exerts a normal force on me, it's because I'm exerting a force on the floor, an equal and opposite force. But again, for free body diagrams, you don't really look too much into that. Speaking of free body diagram drawings, be sure that you can draw them. Typically, all forces originate in the center, or really around the center of mass is a little bit more of a correct way to look at it. And they point in the direction they're acting on the object, not the direction that the object is exerting any force. So let's go back to that example of me hitting a racket. Well, not hitting a racket, hitting a ball with my racket. That's why I was so bad at tennis. I always grabbed a ball and smacked rackets around. All right. One time I was playing a game with... So living in Augusta County, you kind of invent your own methods of fun. So some friends and I were not sitting, we were running around in someone's backyard with a bunch of tennis rackets, and we were playing essentially a game of keep away, where you would hit basically there's one person in the middle and everyone else is around the outside. And it was essentially, if the person in the middle touched the ball with their racket, then whoever last touched it was now in the middle, basically. And at one point I was in the middle and I had this epic jump to try to reach the ball. My friend had the same idea right behind me. She swung down, hit the ball away from me, continued swinging, and hit me in the forehead with her racket, and I bled, and she laughed at me because it looked funny when I put a Band-Aid on. What am I talking about? Okay, so let's say we wanted to do a free body diagram of the racket at the moment it hit the ball. Now the ball gets hit, it goes flying this way, but I don't care about what the ball is feeling. I'm doing a free body diagram of the racket. So from the center of mass, it would have gravity downward. It would have some force from my arm, some applied force pointing up. Then it would have the force of the hit, but because it's on the racket, the ball hits the racket backwards. And this is the moment that it's in contact. As soon as the ball is gone, that F hit goes away. So let me redraw my racket real fast. Once the ball is gone, and this is assuming I didn't follow through like I should have, and I just held the racket up here after hitting it, you would just have these two forces acting on it. So in a given situation, make sure you can draw me a free body diagram. Notice how all my forces were originating on the center. All of them were pointing in the direction that they were exerting a force. So my arm was keeping the racket upward. That's why the main force was pointing upward, when really my arm was attached down below it. All I care about is the direction that the force is acting on the object. Once an action has been completed, no past forces. So it's kind of like when we did that free body diagram interactive. One that a lot of people had trouble with was the baseball player diving and sliding across the ground. They would correctly draw gravity downward, normal upward, and friction to the, let's say he's sliding to the right, friction to the left. But then they would often include an applied force to the right. The main pitfall to keep in mind as you go through these drawings is that velocity is not a force. So the mere fact that I'm moving that way doesn't mean I've got a force pointing that way. So be careful about that. Sometimes it does. If I'm pushing a refrigerator to the right and it moves to the right, guess what? It's got both a force and a velocity pointing that way. So just kind of keep that in mind. FBD drawings are for forces only. It's a very exclusive club. Other vectors try to get in, velocity, but they're not allowed in. Trying to think of another vector other than acceleration that's semi-allowed in. Oh well, angular momentum is not allowed in either. All right. Some tips for drawing free body diagrams. You all pretty much have already got this down from working with most of you all. A lot of times you can just use a box to represent the object. Don't worry about making any sort of complicated drawings, because then your lines might get in the way of your vectors. Make sure you take every force acting on the object into consideration. In fact, I should reword this to say not just every force, but every present force on the object into consideration. If you know that one force is bigger than another, you can use a longer arrow to indicate that. And once again, do not include forces the object is exerting against something else, only the forces on the object. Just some typical free body diagram rules. Any questions up to this point while people furiously write? Cool. Okay. So I'm going to power forward. Once again, this is going to be posted online, so you can go back and finish up your notes that way. When you're doing your free body diagrams, it can be easy to forget a force or to include more than there should be. So take some time to practice with that. I did have a student who said she was going to, and I'd recommend it for everyone if you've not been back for a while, Google FBD Interactive. And that'll give you a bunch of scenarios that you have to correctly put together the free body diagram for. Some people breezed through this in class in a few minutes when we started it. Some people weren't able to get halfway through, which is fine. But now that it's test time, you should probably be able to put these forces together. So that's a good place to go to practice. Forces to not forget is gravity. Weight. The nice thing about gravity is that it always points straight down. And it always has, when you're on Earth, the value mass times 9.81. Another mistake people commonly make is this. The force of gravity is not 9.81 newtons. The force of gravity is mass times 9.81 newtons. altogether, that'll come to newtons. 9.81 is an acceleration due to gravity. And from Newton's second law, F equals ma. So the force due to gravity is the mass times the acceleration due to gravity. Normal force. A quick note about that. It does not always equal mass times 9.81. Sometimes it does. But the only times it does is when the object is just sitting or moving with a horizontal velocity. On a surface, you got gravity downward, you've got normal force upward. And assuming there are no other y forces, then the two of them will be equal. But as soon as you start throwing in another force that has a y component, now the normal force and gravity are not necessarily going to be equal to each other. As soon as you start accelerating up and down, like in an elevator, if I accelerate up, then my normal force had better be bigger than my gravitational force, which is why when you start moving upward, you feel a bit heavier because the floor pushes up on you stronger than it usually does. If I'm accelerating down, then gravity had better be bigger than the upward normal force, which is why when you're at the top and you begin to move down, or if you're moving upward and you start to slow down, in both cases you're accelerating downward, the elevator starts to feel a bit lighter because the floor is not pushing up on you as strong as it usually does. So just be aware of that for normal force. A lot of people see normal, immediately plug in mg and try to move on with the problem. Sometimes that's not quite the case. Ooh, on a ramp. If you're on a ramp, it's not going to be just mg, because mg is now not pointing in the opposite direction as the normal force. Tension. Tension is the force from a rope or cable or string. And it's a pull-only force. So if I've got a string attached to something and it's swinging back and forth, then the direction of the force from the string, the direction of that tension force, is always going to be away from the object. It's impossible for me to get a rope to push something. If you've ever tried that, it's really frustrating. It just kind of folds up on itself, and then it's boring. So a pull only, that means that force will be in this direction, not downward. Friction, we'll talk about in just a little bit. There are a couple of different types, kinetic and static, and you can have some fun with that. And then make sure you include any applied force. This is usually if you've got a person pushing or pulling or kicking or whatever else. By applied force, I pretty much just mean like an other category. And you all know if a kick is happening. Now remember, if I kick a soccer ball and then it travels up in the air and has left my foot, if I do a free body diagram for the ball when it's up in the air, it's gravity only. I don't care that it's still moving upward. My kick has now lost contact with the ball, so you do not include that past force on the free body diagram. Yeah. Yes. The question was, so it's just the moment when your foot leaves the ball, and that's when it's no longer a force. And that's correct. So while my foot is in contact, it's still a force. As soon as my foot is no longer in contact with the ball, there's no kick force on the ball. Yeah. Here's a typical method for breaking down and solving these force problems, like the force fortress today. 1. Set up your coordinate frame. Here's what I mean by setting up your coordinate frame. Decide where you want to put the y-axis and where you want to put the x-axis. A lot of times it's helpful to just do it up and down and left and right. But if you're on a ramp, you're probably going to want to put your coordinate frame somewhere else. Setting up a coordinate frame doesn't just mean, well, a few things to pay attention while you set up your coordinate frame. 1, make sure you know which axis is y and which is x. 2, make sure your origin is at a good spot. A lot of times this would be where the center of mass is on an object. Um, so that way all the forces originate at 0 and point in different directions. Also, make sure you've identified on your y-axis, as well as on your x-axis, what is positive and what is negative. And then make sure you stick with it for the duration of your problem. So if I say, the typical standard is up is positive, down is negative, right is positive, left is negative. And if that's how you want to set it up, great. If I then find a force that's pointing this way, when I break it into my x and y components, I'll see that I get a positive y component, because that component of it is pointing upward in the positive direction. But I'll see that I get a negative x component, because that's pointing to the left. So when I break this vector down into x and y components, my y I would consider positive and treat it as just straight up a positive number. My x I would consider negative and treat it as a negative number in my x list. But that's just for that direction. It's of course going to be different if it's pointing, let's say, this way. Now I've got a downward y, that's negative, and a leftward x, that's negative, and so on and so forth. So just be sure on your picture you take the time to identify what's positive and what's negative in the x and y direction only. That's why I don't generally label forces as positive or negative to begin with at all, because negative just tells you direction. And if it's this direction with one component positive, one component negative, that can get confusing until you break it down. So at the step that you've broken into x and y components, that's when you actually start to assign positives and negatives. So for step 2, in the event that you get a force that's pointing straight up, for example, and I don't even know what the value is, let's just say I know it's a normal force. When I break it into x and y components, a lot of people are tempted to just put the value in both x and y, but that's not quite correct. In the y direction, it is. My full vector is pointing straight upward. I've got that full normal force in the positive y direction. But in the x direction, I've just got 0. So if it doesn't go left or right at all, that component gets 0. If it doesn't go up or down at all, the y component gets 0. And the x component gets the full thing, the full shebang. So most of the forces that you encounter, if you set up your coordinate frame well, should already be just in the x direction or already just in the y direction. So that shouldn't be too taxing of a step. The only times you really need to worry about it are when you've got some sort of an angle that you're dealing with. You'll have to find fx and fy separately. So make sure for step 2 that you're up to snuff on your SOHCAHTOA and right triangle trig. Once you've broken it into x and y components, and what I do is create a chart that leaves me the force, my x component, and my y component. So that way it's just readily available for me to go through. Down at the very bottom, try to get a total of your x's and total of your y's. Remembering again, anything you don't know, just leave it as a variable and then begin to total it up, keeping it as the variable. Don't forget pluses and minuses. This is probably the biggest mistake that happens on these free body diagram problems, is either A, not setting the free body diagram up correctly in the first place, or B, when adding your x's and y's, you just treat all the numbers as positive, and that'll get you into trouble. So don't forget your positives and negatives. Oh yeah, I already wrote that on here. Huh. Now, if you already know the total x force and the total y force, set the sum of each of your individual columns equal to that total value. For example, if it's not accelerating, the sum for both of them should be set to 0. If it is accelerating, you can always use total force. Whoops. Oh no. You can always use total force equals mass times acceleration. That means the force in the x direction equals mass times the acceleration in the x direction alone. Force in the y direction equals mass times acceleration in the y direction alone. So maybe I don't know my total force in the x direction, but I know my total force in the y direction. That'll still allow me to solve for some unknown variables that way by looking at y all by itself. And if you need to find the total force, just like you always do when you've got x's and y's, but not the other, you can Pythagorean theorem that to get the rest of your way there. Sometimes you need to know the total force. Sometimes I just give you the total force or information about how to find the total force and ask you to find a single force within there. So be very careful. These last couple of steps are kind of problem specific. So your last steps will vary based on what your problem asks of you. So pay very close attention. Make sure you know what you're solving for before you try to start. Because you don't want to walk down a long road and then realize you were walking the wrong way the whole time. So just make sure you know what it is you're actually looking for. And if any of the problems give you confusion as to what they're actually asking for, that's when you need to call me over and I can try to clarify the question for you. To say, yes, this problem is looking for normal force. Oh, okay, great. Then you can go and find the normal force. All right. Any questions so far? That was just kind of an ambiguous general step-by-step without an example, but okay. Upon asking questions, one student hit another student with a pencil, so I think that means there are no questions. Excellent. So ramp problems, we did a few of these. I like these ones. These ones make me excited because the easiest way to solve them, there are a bunch of different ways to solve them, but the easiest way to solve them is this. Align the y-axis to be perpendicular to your ramp. Align the x-axis to be parallel to your ramp. So let's say I know this angle down at the bottom here, this angle theta. The first thing I'm going to do is draw my new x and y axis. There's my y falling right on top of that normal force. There's my x falling right on top of the force of friction. Then you're going to shift your view. Because again, these problems are easiest the fewer forces that you need to break down into x and y components by yourself. It's a lot easier if they're already pointing in x or already pointing in y. Most of these forces are either parallel to the ramp or perpendicular to the ramp. Oh, and by the way, one thing that I noticed people were doing incorrectly today, if a box is just sitting on the ramp, basically the direction of the force of friction was giving people problems. If it's just sitting on the ramp and that is it, that's all that's happening to it, the force of friction is going to point up the ramp. Ask yourself when you decide it's time to start putting friction in here, if friction was not present, which way would the box move? And that's just up to you to use your common sense for that. In this case, if friction's not present on the ramp, that sucker's sliding down the ramp. So because of that, friction's got to be pointing up the ramp. I think where people were getting confused when they did that activity today was because we did a previous example where I had a ramp, but I actually had, it had normal force, great, it had gravity, great, but I actually had someone pulling up the ramp. And in this case, if someone is pulling up the ramp, friction's going to try to fight that. So now friction will switch its mind and point down the ramp, because friction always tries to oppose your pull that way. So yeah, just be aware of that. But in the example that there's no one pulling on it and the box is just sitting on the ramp, friction will hold it upward. So you've slapped your X and Y coordinate frame on here. Now you need to shift your view. I like to redraw the free body diagram with my Y-axis pointing straight up and my X-axis pointing horizontal, just because that's what I'm comfortable with. So by shifting my view, basically that means I'm grabbing the picture and I'm rotating it. Let's see, the X-axis is usually horizontal, now it's pointing upward. If I grab this ramp and pull it down an angle theta, then I'll get my X-axis horizontal again. To do that, I'd have to bring all these axes around an angle theta, which means all the forces are pulled an angle theta. In this picture, in the clockwise direction. So when I do that, I'll get my normal force pointing straight up the y-axis. I'll get friction pointing straight along the x-axis. I'll get my weight is now pointing down this way. It was pointing straight down. Then I shifted it clockwise an angle theta. So that's how I know where to put my angle as well. That's just the angle of the ramp. From there, you can break your gravity vector into its y component. And if this thing's not accelerating, then this y component and this y component had better be the same. And get your x direction. And if it's not accelerating, this x component and this x component had better be the same thing. Be sure you pay attention to where the angle is so you know where to put your sine and cosine properly. Cosine goes with the adjacent to the angle. Sine goes with the opposite. Right. And then, once you've got this all set up, now it's time to go through all those steps on the previous slide and go force by force and break that down. Nice. Be sure you're aware of this idea of weight versus mass. I mentioned it just in this last problem. My weight is pointing straight down. That's because weight is a force. It's a special name given to the force of gravity acting on an object. Weight. It's just mg. Your mass is just m. Your mass in kilograms, which is the same everywhere in the universe. So if I went to the moon, my weight would change, my mass would not change. And mass is a scalar. So weight has direction, mass does not. I'm just doing a quick pause to let people write real fast. I should have elevator music with me at all times. So when I put everyone on hold, they have something to listen to. see how our recording is doing. Make sure that I'm still actually streaming on YouTube. Hey, I am still streaming on YouTube. Good news. Someone asked, has it ever happened where most of the way through you realized you didn't hit play? When I was live streaming, I think it was my second year here. I was using a program called Livestream, and we had an event on the physics platform the same time we had a review session. So I had to take my review session and move it to the grid, and I did it there. And it was my first time using that computer, and I forgot to hit the unmute button on the microphone. So I went through the whole review session, and my microphone was muted. So people were watching it at home and came in the next day and said, "There's no sound on your review video," and that was really frustrating because then I had to kind of re-record my own review on my own time and send that out separately, and that was rough. So I think it's working okay this time. All right. Well, then we moved on and we talked about friction. So there are two types of frictions. There's the static friction and kinetic friction. Go back and look at my video all about the Friction Brothers for some beautiful drawings of knights. And you'll see what I mean. Static friction is the more confusing of the two. Let's say there's a box, and I push it. It's a huge box. Oh, that is weird. I twist and push it, apparently. With 30 newtons of force, and it does not budge. What is the value of the static friction force pushing back on it? Yeah, 30. If it's anything less than 30, that means I'm accelerating to the right. If it's anything more than 30, that means I pushed on it and the box accelerated to the left back toward me, which also doesn't happen. So that means that 30 newtons falls somewhere in this range. I don't know where it falls in the range. Maybe it's over here, or maybe it's right near the maximum value. I don't know. But all I know is 30 newtons was not enough to defeat static friction. So I muster up a bit more strength. I twist myself even farther over, and I push at 40 newtons, and it doesn't budge. This means now static friction is 40 newtons. Okay. Basically, I have no way of knowing what the maximum value of static friction is until I get it moving. The moment I hit a force and it just begins to budge, that's how I know static friction has reached this value. So 30 fell somewhere in this range, 40 fell somewhere in this range. Let's say I finally push with 70 newtons, and that does it. That gets it to start budging. So at that point, static friction hit 70 newtons and then was like, ugh, and failed. So I would say 70 newtons equals my coefficient times my normal force. Notice how earlier I was pushing at 30. I did not set 30 equal to my coefficient times normal force. Earlier I was pushing at 40. I did not set 40 equal to coefficient times my normal force. It's just some value in that wide range until I hit the maximum. Then I can set it equal to that. Yeah. Basically, continue to push until it starts moving. Yeah. Yeah. Or right. So if I just told you I pushed with 60 newtons and nothing happened, you would not be able to tell me what the coefficient was. You could tell me what the coefficient was at least greater than. It had to be this value minimum or could be more. But you wouldn't be able to tell me what it was until it started budging. Or if you wanted to find that max value, let's say I gave you the coefficient of static friction, you knew the normal force on it, then you could calculate what that max value is without actually pushing it and letting it budge. You could do that. Okay. Now, at this moment that the push defeats static friction and it begins to slide, that's when kinetic friction takes over. Um, For those of you that did the kinetic friction cave problem today, you noticed that you had to push with, I think it was like 608 newtons to get it to move in the first place. Then part B said, if you keep pushing at the same force, how much will it accelerate? Once I've gotten it moving, I know I've got kinetic friction acting against me. The beautiful thing about this is that kinetic friction's not a range of value. It's not going to be anything from 0, go through 30, go through 40 till you get up to a big force. It's just going to be this value. So take your kinetic friction coefficient, multiply it by your normal force, and I think in the problem that I gave you, I don't remember what the backwards force was. It was something like 400. Shoot, I don't remember. I think it was 0.42 times 981. Yeah, in the problem you had 412 backwards. So from there, if I got 608 forwards, 412 backwards, I can find my total force as just 608 minus 412. And from there, I can set it equal to mass times acceleration. So you can use this equation of kinetic friction to figure out one of those forces in your free body diagram, usually. If you need to find the acceleration of something, make sure you've taken all the other forces into account as well. But that is it for kinetic friction once it's sliding. Push any harder, you speed up. Push any lighter, you slow down. Push at exactly the friction rate, and you go at a constant speed. And typically, the coefficient of static friction is greater than the coefficient of kinetic friction. It's more difficult to start something sliding than it is to keep it going once it's already sliding. And that's kind of why I did part B in that friction cave as well, was to show you that if you kept pushing at that max static friction force, it's actually more than the kinetic friction force. That's why you're going to speed up and have an acceleration in the first place. All right, then we finally, Isaiah, yeah. Yes. Right. Right. So in the ramp problem that I gave you all today, the force fortress, you would have to go back to your ramp drawing, which, do I still have that saved on here? No. You can use the, that's actually a really good point, and I'm glad you brought that up. This is not the only way to find the value of friction either. So for the force problem, it wasn't kinetic friction, it was static friction because the box was just sitting here. But once you broke it down and you had your gravity broken into x and y, you had your normal, and you had your friction. Because the box wasn't moving in the problem, I could just take my mg sine theta and have that equal to the force of static friction, because the box wasn't moving. So the x components had to be equal. Is that always true? When the box isn't moving and it's on a ramp and there's no other forces acting on it, then yes. Yeah. Yeah. So you can find the value of friction forces through your regular force diagram analysis. There's nothing wrong with that. And in fact, the force of static friction that you found in that problem wasn't even necessarily the maximum value for it. You found just one of those middle forces, somewhere between 0 and coefficient times the normal force. So you can always use free body diagrams to find individual forces, even friction. You don't have to use these equations to get there all the time. All right. We talked about the difference between a period and a frequency. Frequency is the number of circles you complete in a second, and period is the number of seconds that it takes you to complete one circle, which means they're perfect inverses of each other. So if you're given a frequency in hertz, you can always find the period. Just take 1 over the frequency and you've got it. If you find the period in seconds, you can always find the frequency. Just take 1 over the period and you've got it. Just be very, very careful when you look at wording of circular motion problems that you know whether I'm talking about a period or a frequency, because those can be really easy to mix up if you just breeze through the problem quickly. Um, so go back, double check, look at the wording, and ask yourself, is it circles per second or seconds per circle as you go through this? We talked. Yeah, there you go. Sure. Oh, yeah, you can just head out whenever you need to. We then talked angular velocity versus linear velocity. So angular velocity is in units of radians per second. And here's the most important part that you'll probably want to take away from this slide is this right here. A circle has 360 degrees. Another way to measure it is in radians, not degrees. One complete circle, 360 degrees, is 2 pi radians. So I can always tell the angular velocity of something if I count the amount of time it takes to finish a circle. Um, I'll just take 2 pi, divide it by the period, and we're done. I've got my angular velocity in radians per second. So think about what the units actually mean, and that'll help you. That'll help you get there. So it's 2 pi over t, um, where t is the period in seconds. But since the period is just 1 over the frequency, I could rewrite this as just 2 pi f, where f is the frequency in hertz. Thank you. No. And don't forget, these are posted online too, so if you miss something, you can always catch it there. Right. Yep. If I give you a frequency, use 2 pi RF. If I give you a period, use 2 pi over t. Or sorry, 2 pi f, not 2 pi RF. That's regular velocity. Right. Linear velocity. And please don't write down the words average tangential velocity describes how far an object, because that will take forever and we'll just be sitting on this slide for a long time. So again, these words are available to you already on Canvas. Um, the main takeaway that you're going to want to get from this is this here. You can find the raw speed that something's moving as it travels around the circle as 2 pi r over t, where again, t is the period in seconds, or you can find it as 2 pi rf, where f is the frequency in hertz. R, don't forget, is the radius of the circle. That'll be measured in meters. This can be helpful if you ever find yourself needing to solve for centripetal force, but you don't know the velocity to begin with. Since centripetal force is mv squared over r, you can always use this to find what that v is. And that can be helpful a lot too. We use this in the Jupiter simulation. The most common mistake in the Jupiter simulation was people just taking the radius and dividing it by the period rather than the circumference. So just be aware of that. Another super important thing to remember from this slide is how to relate linear velocity and angular velocity. So here's your linear, that'll be in meters per second. Omega is your angular, that'll be in radians per second. And r is going to be in meters, the radius of revolution. V equals omega r. Brilliant. Three things to remember about centripetal force, sometimes called radial force, but I usually use centripetal. One, it always points toward the center of the circle. So when you do your free body diagram of an object going in a circle, one of those forces at least should be pointing directly toward the center of the circle. Once you've identified what that force is, and ask yourself, is it actually causing the object to go in a circle? If it meets both those check marks, then you can take whatever that force might be and set it equal to mass times velocity squared over r. Sure. Well, you can, I mean, not necessarily how you can set it equal to. Okay. So the question is, can you show us how you can set it equal to something where the masses cancel out? Yes and no, because it doesn't happen like that all the time. So for example, if I'm spinning something over my head like a lasso, then the force of tension would be the mass of whatever's on the end of that string times v squared over r. I got nowhere to cancel my masses. The one example I think you're thinking of is orbit. When something's in orbit, it's the force of gravity that's bringing it around. I'll call this mass big M, I'll call this mass little m. And when it's the force of gravity, when gravity causes something to go in a circle, then just like you can with any other force, take that force of gravity, which you can find as g times m1 times m2 over r squared. So g times the central mass times the satellite over r squared. Take whatever force is causing it to go in a circle and set that force equal to mv squared over r. Yeah, big G is 6.67 times 10 to the negative 11. I'll give you that value on the test, by the way. Any major constants that you need to know, I'll try to give to you. Newton meters squared per kilogram squared. Okay. And here, Noah, is where your masses might cancel. So when something is circling something else in orbit, it doesn't matter what the mass of that circling thing is. Its velocity will stay the same as long as its radius stays the same. Yeah. But again, that's only when gravity causes something to go in a circle. So if, let's say, an asteroid is just chilling nearby and then it starts to speed up and head toward Earth because of Earth's gravity, then I cannot set it up this way because that asteroid's not moving in a circle around the Earth. So just be aware of that. Or me standing on Earth right now. I'm not going to set it equal to mv squared over r because I'm not moving in a circle around the Earth. So it's only when it causes it to go in a circle that I can set this equation up. Hey. Oh, which brings me to Newton's universal gravitation law. This is the force of gravity between literally any two objects that have mass. So your checklist, does object A have mass? Yes. Does object B have mass? Yes. Awesome, they're attracted to each other gravitationally. And you can find the value of it by taking big G, multiplying by the product of the masses, and dividing by the distance between them squared. yeah. Yeah, when you are like on Earth's surface, you can take a shortcut and just use mg. But it works if you're on Earth as well. It also just works everywhere else. The big equation. Where do you use F equals ma? What do you mean? Oh, instead of calculating the force of gravity as g m1 m2 over r squared, if I'm on Earth, I can already tell you that the mass of Earth over the radius of Earth squared times g comes to 9.81. So yeah, m1g over r squared would equal 9.81 on Earth's surface. What on Earth? Okay. The only time I would set this equal to mv squared over r is if I'm right above Earth's surface and I'm somehow orbiting it while right above Earth's surface. Um, the only way to do that is to have a really, really, really big velocity and somehow not hit anything as you go, and maintain that velocity. But if you could do that, then yeah, you could set those forces equal to each other. It's probably not going to happen though. By the way, you can find the force of gravity or the acceleration of gravity on any planet by taking this force and setting it equal to one of the masses times acceleration. Solve for the acceleration that way. So I think I asked you what is the force of gravity on the moon at one point. You would just have to take the mass of the moon, the radius of the moon, and g, and you can solve for that acceleration value. And it comes to not 9.81, it's like 1.62 or something like that, meters per second squared. Yeah. Whew. And that is it. Yeah. Any secret things on the test? Not that I know of, but I will let you know if I discover something. Yeah. The curviest ball on the test is not. Well, I can't ask you about curveballs yet. We've not learned the Magnus effect yet. Yeah. Tracy, yeah. Okay, let me stop recording. Let me go to screen one.